Okay, thank you for introducing me, Tobias. Hello, I am Shinkuk Choi, tech lead at Nota AI. First of all, thank you so much for having me here today. It is such a pleasure to work with ARM and present our research work to all of you. Before we go any further, I would like to give a brief introduction of what Nota AI does. Nota AI was founded in 2015, and since then we have worked with many clients and partners, including Samsung, Naver, Kakao, and LG, who also became our strategic investors. Nota AI, headquartered in Seoul, Korea, has office in Berlin and Germany and San Jose, the United States. And we are a technology-driven organization consisting of about 80% of the R&D team. Our core technology is AI model optimization, and we do offer two types of services to our customers. First, our flagship product, Netspresso, is a proprietary hardware-aware AI optimization platform which automates the whole process of AI model development process from building AI model to deploying on the device. Netspresso provides AI models customized for the target device, and it supports a wide range of devices to meet users' requirements. It not only minimizes human resource, but also a time to market to make AI into production faster. Second, we provide edge AI development and professional optimization services. With Netspresso, we were able to develop applications for a diverse range of edge AI solutions, including intelligent transportation systems and driver monitoring systems. Our solutions enabled our customers to overcome stringent memory and power constraints while satisfying their target performance. Today, I am going to share my experience working with ARM U65 NPU, how we approached it from a hardware-aware perspective, and how we could achieve such a result using Netspresso. The number of float point operations, flops, is a widely used metric to measure computation complexity of the neural network. However, flops is not linear with computing speed or latency. If you take a look at the figure below, you can observe that even the network with similar flops show different speeds. For example, if you look at the red box, you can see that 4 different networks with the same 150 megaflops have different batches per second. In other words, to design a low latency neural network, you should not be obsessed with improving flops only. For most devices, improvement in metrics like flops or the number of trainable parameters is not directly correlated with the improvement in efficiency of the network. For example, there is a graph comparing fused IBNs, which replaced its pointwise and convolution and depthwise convolution layers with a standard convolution layer. If you see the graph, the leftmost bar and the rightmost bar shows the same latency, while fused IBN has 7 times more parameters than the original depthwise IBN. Therefore, when designing an optimized neural network, it is also important to take both the neural network itself and target hardware's characteristics into consideration. In order to study the previous problems, we worked on a virtual environment called ARM virtual hardware for using ARM Ethos U65 NPU. ARM virtual hardware, AVH in short, is an evolution of ARM's modeling technology. It delivers models of ARM-based processors, systems, and third-party hardware for application developers and SoC designers so that they can build and test software before silicon and hardware availability. AVH is a fixed virtual platform, which is a digital twin of the board with Ethos U65 and Cortex M55. Corestone 300 is also available on AVH. For the device configuration, main units were selected as 256, and the memory mode was selected as dedicated SRAM. And lastly, the optimization method was selected to focus on the performance. So let's take a look at ARM Ethos U65 NPU. It is a micro NPU which doubles the machine learning performance of Ethos U55 while maintaining U55's energy efficiency. We have selected Ethos U65 as we believe that it could help us to contribute to bring AI everywhere. ARM Ethos U65 NPU is a microprocessor that specializes in the acceleration of neural network processing. It consists of main units and element-wise engine as computation units. And each memory is divided into internal memory and external memory. In external memory, SRAM and DRAM operations are performed through an external bus. The strength of Ethos U65 NPU is that it has an extra element-wise engine besides a main unit. The engine serves as a key component accelerating the computing speed of element-wise operation. When someone tries to take the best use out of Ethos U65's capabilities, there are two main constraints to keep in mind. One is an activation buffer size, and the other is a size of AI model. For activation buffer size, when the memory mode is set to a dedicated SRAM mode, the arena cache size of SRAM is limited to 384 kilobytes. Kilobyte and megabyte equal to 2 to the power of 10 and 20 bytes, respectively. They are more precise units to measure the memory size than kilobyte and megabyte. In other words, when the activation buffer size exceeds 384 kilobytes, it utilizes DRAM, resulting in a dramatic increase in latency. Moving on to model size part, Ethos U65 has a memory size of 32 megabytes. The device will not be able to carry out a computation if the sum of the model size and the activation buffer size is bigger than U65's memory size, which is 32 megabytes. Therefore, without considering these two constraints, it is impossible to design an efficient neural network optimized for Ethos U65. For a better examination of Ethos U65's characteristics, we ran experiments with several convolution types and building blocks. For convolutions, various convolutions such as group convolution, ghost convolution, and blueprint separable convolutions are adopted, which are variants of the standard convolution layer. On the block level, we employed fused IBN, fused group convolution IBN, and maxpool IBN. To be more specific, Fused IBM and fused group convolution IBM are blocks that replaced both pointwise convolution and depthwise convolution with standard convolution and group convolution, respectively. And maxpool IBM is a variant of IBM that replaces depthwise convolution with maxpool. We measured how latency on Atos U65 varies according to each different configuration of convolution types and building blocks. First, if you take a look at the bar graph on the left side, it portrays the latencies for 4 different convolution types. And you can clearly observe that the latency changes as height, width, and channel value changes. In addition, you can also notice that the level of change in latency differs depending on the convolution types. The figure on the right side describes the relative latency of the IBM variational blocks normalized to the latency of the original IBM blocks. If we compare blocks with 32 channels and 64 channels, there is a little change in the normalized latency values for fused group convolution IBM and maxpool IBM, depending on the configuration. However, there is a surge in the normalized latency value for fused IBM in an indigo blue color from 1.5 to 3.3, which has increased more than twice. One of the reasons why there was a significant rise in the normalized latency of fused IBM compared to other blocks is the increase in max. Replacing pointwise convolution and depthwise convolution with standard convolution results in larger max. However, it does not fully account. It merely affects, which might increase the latency only up to about 2 as much as colored on the bar as indigo blue. Then, what caused such a drastic shift? The red part of the bar happened as the activation buffer size exceeded 384 kilobytes as the channel size increased up to 64, which led to usage of both SRAM and DRAM at the same time. To sum up, it is important to consider the configuration of blocks in order to achieve faster inference on the actual device. In previous slides, we have covered the importance of taking a hardware-aware approach, the characteristics of ARM Atos U65 NPU, and the relationship between latency and various blocks. Now, I would like to illustrate how we could create a powerful and efficient network optimized specifically for Atos U65. How we could achieve such results and what kinds of tools and methods we used. As I mentioned earlier, Nota AI has its unique hardware-aware AI optimization platform called Netspresso. Netspresso is capable of resolving AI-related constraints in business use cases. It enables cost efficiency and enhanced performance by removing the requirement for high-spec servers. Also, it can deal with other issues like network connectivity, high latency, and personal data breaches. Netspresso accelerates the AI model development process by automating the repetitive steps. A user only needs to set a target performance and a target hardware as input. And then it automates the whole process for a user to build an optimized AI model. As you can see from the diagram on the slide, The target hardware was set to Atos U65 using AVH for the experiment. Netspresso is modularized into three sub-modules, model searcher, model compressor, and model launcher. These three sub-modules helps users to build, optimize, and deploy AI models as efficiently and effectively as possible. This slide shows what integrating ARM virtual hardware platform with Netspresso would look like. A user will be able to select an option, ARM virtual hardware under the target device, and optimized AI model for ARM devices. The first submodule, model searcher, is a hardware-aware automated tool which automatically searches optimal AI models for the target device based on a given dataset. For instance, if you choose AVH as your target hardware, model searchers would search optimal network architectures for ARM devices such as Atos U65. Model searcher is able to significantly shorten AI model development time from months to a couple of weeks by producing near production-ready AI models. Furthermore, the outcome models show better performance than most of SOTA models in terms of latency, power consumption, accuracy, and others. We could help users achieve these by leveraging our hardware-aware approach to create a model. Moving on to the second submodule, model compressor, is a ready-to-use toolkit automating AI model compression process. When an AI model is given as an input, model compressor performs model profiling, compresses it, and provides the outcome model, which is improved in all aspects, such as latency, power consumption, memory footprint, and others. It not only supports various deep learning frameworks, such as PyTorch and TensorFlow, but also supports all kinds of convolutional neural network architectures. Model compressor recommends on optimal configurations for a given model, which enables state-of-the-art performance even for users without any AI expertise. It can eliminate months of paper implementation time and minimize loss of information. Lastly, the third submodule, model launcher, helps users to accelerate and deploy the model on the extra hardware at ease. While AI researchers are experts of neural network architectures, most of them are not experts of hardware. Model launcher helps AI engineers to easily convert and run AI models on the device. Moreover, a user can measure the benchmark result on actual hardware, such as latency and power consumption, instead of simulated values. Offering various converting methods, a wide range of devices, and model packaging, Model Launcher is a great tool to embed AI applications. The diagram shows how Netspresso operates and where each module gets involved in the traditional deep learning workflow. In a nutshell, Netspresso is a one-stop shop to build, optimize, and deploy optimized hardware-aware AI models on the ARM virtual hardware. Then, we are going to present the results of AI models built with Netspresso in the ARM Atos U65 aware approach. We are going to share the results for the image classification task, which is one of the most widely used computer vision tasks. The data set used is SciPy 100, and the baseline models are VGG19, ResNet 50, and MobileNet V1. In the figure on the right side, the indigo blue color represent the latency of the original baseline models, and the light blue color represents the latencies of the optimized model using our Netspresso. You can observe an obvious enhancement in latency after using our Netspresso. To be more specific, for VGG19, max, the number of parameters, and the model size were all significantly decreased, boosting the inference time up to 7 times, only with tiny drops in accuracy as much as 1.5%. MobileNet V1 also demonstrates outstanding improvements in all aspects, leading to 5 times faster latency. On top of that, even the accuracy has slightly increased. Here are the results obtained from using the image-of dataset. On the table, you can see that there is no latency value for the original model. The reason is that when the input image size is set to 224 by 224, the model size of the original VGG19 model becomes 32 megabytes, which equals the memory size of Atos U65. However, it exceeds the Atos U65's memory size of 32 megabytes when the activation buffer size is added, which leads to out of memory and not being able to run an application. By compressing with Netspresso, the model size could be minimized to about half of the original size, so that the sum of the model size and activation buffer size do not exceed 32 megabytes. Only then we could run VGG19 on Atos U65 and measure the latency while maintaining the accuracy declining by only 0.4%. In conclusion, with ARM virtual hardware platform and Netspresso together, we were able to produce remarkable optimization results for Atos U65 NPU both efficiently and effectively. Last but not least, I would like to highlight that we are willing to offer free trials exclusively to those who visited and watched today's Tech Talk. You can come and apply from the link on the slide, netspresso.ai. If you visit our website, you can see the performance tables, and moreover, you can download and use our off-the-shelf models for free. For example, we have a ready-to-use people detection model optimized for Raspberry Pi 3B+. So if you are interested, you are more than welcome to use them. Appreciate it. Thank you.
Amazing. Thank you so much, Jungkook. I really appreciate it. And what fantastic results. Fantastic results on U65, and a great example of how important model optimization, model compression is in an AI workflow. So we have a few questions. I've got a couple of questions, and I'd invite the audience to please use the Q&A box in the menu below, and we can ask those. I have a couple of questions from my side. Is when can we use ARM virtual hardware with Netspresso? When will it be available? When will Netspresso on ARM virtual hardware be available?
our virtual hardware is already supported on internal product. And we plan on launching our commercial version in early Q4.
Not long then. So keep an eye out for some news from Nota in the next few months. It will be very, very exciting. Very exciting indeed. Now, there's a couple of questions come in and I will make sure we get to those as well. You talked about the hardware aware approach for U65 and for image classification. Is the hardware aware approach you spoke about applicable to tasks other than image classification?
Oh, sure. It is possible to apply the hardware-aware approach for various computer vision tasks, such as object detection, segmentation, and super resolution, and so on. However, only some features are available in the current Netspresso version, and we are going to support more features in upcoming product releases.
Brilliant. Thank you so much. And one other question I've got as well is, with the Netspresso results you showed, the Netspresso results, how did the model searcher and the model compressor apply that hardware aware approach?
Yeah, that's a good question. We appropriately used both model searcher and model compressor to achieve the result. We have run experiments with various factors related to hardware efficiency, and based on the findings, we could customize the networks for our U65 NPU. I apologize that I am not able to disclose the details. And the model searcher currently only supports object detection, but image classification and segmentation will be supported later. And model compressor supports any CNN-based networks for computer vision tasks.
Thank you. Thank you, Shin-Kook. Let's get to a few questions that have come in from the audience. So please do keep those coming in and hit the little thumbs up if you want to make sure that a particular question you see is at the top. I'll pick one of these. Does the network search need a predefined architecture and trained weights, or is the search based on accuracy and speed constraints? That's the question at the top. So does the network search need a predefined architecture and trained weights, or is it based on accuracy and speed constraints?
Oh, thank you for your great question. Our search algorithm is based on neural network, a neural architecture search. It means that we investigate new model architecture based on the target hardware, target accuracy, and speed constraints.
Thank you. Thank you very much, Shin-Kook. So I'll just tick that one off. Let's have a look. Are you also quantizing the model? If it is 8-bit TF Lite, are you using XNN pack? The question at the bottom. So are you quantizing the model as well? If it is 8-bit TF Lite, are you using XNN pack?
Yes, I use the 8-bit TF Lite model because ARM-SU65 only supports 8-bit TF Lite model. And so I convert the model using Vela compiler. Yes.
And are you quantizing as well? Quantizing the model?
Yes, quantized model. 8-bit quantized model.
Yeah. Thank you for that. And what deep learning runtime, e.g. TF-Lite, ARM-N, or something else, is used in running the models on the hardware?
In our Netspresso, TF-Lite, TensorRT, and OpenVINO is currently available, and the other framework is going to be added to.
Brilliant. Thank you for that. So do keep your questions coming in. I've just seen a chat message as well from Bo-Keyon Kim. Yes, I think we've answered both of those questions, Bo-Keyon Kim. If you feel we haven't, do please just message on the chat. But I think we did cover those early on, the questions I had as well. So, but do keep your questions coming in. Do please use the Q&A box. And apologies, I missed that one in the chat earlier on. I've got another question actually, which is, do you perform the optimization process on the target device, or kind of in the cloud, or a high performance processor?
It depends on what kinds of optimization process is applied. Most of the optimization techniques are performed on cloud or high performance processor, but device specific techniques such as quantization method might be done on the target device.
Brilliant. Thank you, Shin-Kook. We've had a question come in around different models. Are there any compression and speed up numbers available for mobile net models with larger data sets like ImageNet? So compression and speed numbers, so latency numbers for mobile net models with larger data sets like ImageNet. Do you have anything for those?
Yeah, sure. I just showed the result of VG19, but mobile net models can also can also be compressed and speed up, like with larger data set, like ImageNet. In our result shows using ImageOf dataset.
And do you have any numbers on that specific to ImageNet and with MobileNet? Do you have any how much faster it was with your technology? Have you used your technology on MobileNet models?
I don't think the value now. And
that's fine. I think if we can ask them to reach out to you. If we can ask them to email you afterwards if you don't want to put you on the spot trying to remember numbers. It's okay. We can if that person in question just wants to email me or email Nota directly, we can find out those numbers for you. That's no problem.
Yes. You can contact us and we can disclose the number to you.
Thank you. That'll be good. That'll be good. So let's then have a look at what does the model launcher specifically do after model compression?
Model launcher. Well, model launcher is support converting and packaging, packaging, and we can use the benchmark using a model launcher on real device.
Got you. Thank you, Shin-Kook. And do keep your questions coming in. In terms of I've actually just thought of something. For the model you mentioned, I think you might have mentioned it, but I might have forgotten. What is the output format of the model? What's the output format of the model itself?
It depends on the target hardware and the purpose. If you use model searcher, the output model type can be TensorRT, TensorFlow Lite, or OpenVINO. And if you use model compressor, then the model would be in retrainable model format. And if you use model launcher, the output would be an executable file such as Python wheel file.
Gotcha. Brilliant. Thank you. That makes sense. And we've just had a question come in around the compilation block, which I think you showed on one of the slides. So this person's asked, what is the need of the compilation block?
I don't get what compilation block means. Could you explain more about that?
Yeah, if the person who's asked the question, if you're able to elaborate more, but I think it was on one of the earlier slides. I'm just having a look, which might have been a compilation block, or it might have been the neural network block diagram that they were talking about. Yes, can you remember which, sorry, well, you can put it in the chat to whoever this is. Apologies, I don't you having to ask multiple questions. You said in the picture, there's a compilation block. You're referring to slide 20. So back a couple of slides.
Slide 20.
Oops. I can't see compilation.
I can answer for that question. Yes. As here, the compiling block or compilation block means that we are converting the model, and the model was trained on PyTorch or TensorFlow, and we need to convert it to the hardware OL platform, such as TensorLite or TensorRT. So we regard this process as compiling block.
Gotcha. Makes sense. Makes sense to me. I double check with the person in question. If you've got any more questions, do keep those coming in. Brilliant. Thanks. Yeah. Got it. Fantastic. No, it's great. And it's fantastic to also see, as I said, that this will be available in the next few months on ARM virtual hardware. So if anyone's interested in ARM virtual hardware, I'll paste a link in the chat very shortly where you can find out more about how you can use ARM virtual hardware, whether it's our Corestone pre-integrated, pre-verified IP or our third-party hardware as well. So you can absolutely go and use that. Any other questions? Any final questions before we wrap up? We've just got time probably for one or two final questions for Shin-Kook and team. I know it's very late for them as it's quarter to 1 in the morning tomorrow. So, but they very kindly stayed on this late. So any final questions for Shin-Kook and Tae-Ho? I'll just remind folks as well, if anyone's got any final questions, that we've got an AI Tech Talk in 3 weeks' time before our summer break. So that's from Raspberry Pi, AI on Raspberry Pi. So do check that out. It's just gone live on arm.com/tech talks. So do check that out. And we, love to see you there and see you at our upcoming Tech Talks. They're really exciting. So I think that's the last questions come in. So Shin-Kook and team, thank you so much for a fantastic presentation. It's been great working with you on ARM virtual hardware and your integration. I'm really excited to see it come to life in the next few months. So we'll keep an eye on that, and we look forward to seeing more of that on ARM virtual hardware. As ever, do get in touch with myself or the Nota team for any questions about today's content. We'll be happy to help and direct you where we can. As ever, if you've got any questions or anything on that sort of things, do get in touch with us. But also, if you want to find anything else out about our AI Tech Talk series, head to arm.com/tech talks. All our upcoming talks will be on there. We'll get the slides from today and the recording. We've been live streaming to YouTube, so I forgot to say hello to folks on YouTube, but we've been live streaming there as well. So do check out the recording. It will be live immediately, so you can go and catch anything you missed on there. And we'd love to hear from you if you've got any questions, comments, or otherwise. So Shin Kook, Taeho, and the team, thank you so much for a fantastic presentation. And to everyone watching, thank you again for watching, and we'll see you again soon. Thanks, everyone.
Thank you.